precise definition of a limit explained again, because I don't think my last video was that clear. So here's what we're gonna do. I'm going to draw a x and y Cartesian coordinate plane, and let's just do the function x, y equals x, which means that x and y are the same thing. So if it's 1, then y is also 1. If x is 2, then y is also 2. I'm sure everyone knows what a linear line is. Or a line is. So what is the epsilon delta definition? So as we remember, if we use the limit rules, the limit as x approaches a of x is always just going to be a. So simply let's reassign this as the limit x approaches 2, x equals 2. So if we assign this as 2 and this is 2, the limit as x approaches a from either side is going to be 2. So that is the limit there, simply put. So now here's what we're going to do. We're going to extrapolate this further, and to do so, we're going to use an epsilon and delta definition. Now this is called the precise definition of a limit. So it states that if epsilon is greater than 0, comma, the limit, which is denoted as L plus or minus, a function's output from L has to be less than epsilon, which means that, I'll explain that later actually, and x minus a, which is the limit input, has to be greater. Let me write that again. Has to be 0, and the x minus a has to be less than delta, which is another number and symbol. And I can't really explain it that well. So let's go over what this definition is. So f of x minus L is less than epsilon. So what does that mean? So epsilon is any preassigned distance from the limit value. So theoretically, you can denote it as infinite, or you can denote it as however big you want. So I can literally denote epsilon as right here, 2 plus epsilon, or I can even denote it even further, 2 plus epsilon, and further and further. But for simplicity, I'll just denote it as pretty small. So actually, let me erase this because I want symmetry, and I don't want the other one to be at the x-axis or the y-axis. So do 2 plus epsilon and 2 minus epsilon. So what does this mean? So f of x is the function output, so it's going to be y here. So any minus L, which is the limit value, which here will be 2. So y minus 2 has to be less than epsilon, and epsilon is that preassigned distance. So remember, this is the distance. Absolute value simply gives you the distance. So for example, if we have a number line here from 4 and 2, the distance between these two is just going to be 4 minus 2, which is equal to 2. But what happens if you have 2 and 4? We go from 4 to 2 to 4. Technically, if you do that formula again, you'll get negative 2. But we know that you can't have a negative distance, so we absolute value it, giving us positive 2, meaning that there's a distance of 2 between these 2 points, which makes sense logically. So that's why we absolute value it. So remember, f of x minus L simply gives us how far or how close an input value is to the limit value. That's all it means, or how far it is. Same thing, the distance between a function's output and the limit value. So here, it would be y minus 2 is less than epsilon. And x minus a is, so remember the limit notation is this right here. So x minus a will then give us the distance from x to a, and that is denoted as less than an epsilon value. And it also has to be greater than 0. Here it doesn't, because we're given that epsilon is greater than 0 in the definition, but here x minus a has to be greater than 0, simply because x cannot be at a itself, because the limit is evaluating what happens when the function approaches a, rather than being at a. So if it was a, then it would be a minus a, which is the same thing as 0, and you can't be at the a value because the limit says you can't. So what we're going to do is we're going to extrapolate these y values out. So 2 plus epsilon means that the limit plus the epsilon value is going to correspond to right here, and 2 minus epsilon is going to correspond to right here. Now we notice that also this isn't really drawn to scale because 2 is not on the y value, so it's probably going to be like right there. So 2 minus epsilon. And here, so what we are finding is simply 2 plus delta and 2 minus delta. That's all we're finding. So I'm going to explain it in simple terms now because we used some very hard notation. So simply put, let's draw a function here, y equals x again. If the limit of a function is this value right here, L, then we can apply a range, and that range is going to be any arbitrary range, and the range is going to be L plus epsilon, L minus epsilon. So simply, we are finding an x interval that matches this y interval. In other words, if someone says, if the limit is between these two, if the limit is between this and this, find me an x value that will correspond to that same interval. So there's a challenger, which is what a lot of people will use in terminology. There's a challenger that says, I bet you can't find me an interval that matches the y interval. And here, actually, let's change this function a little bit because it looks like L minus epsilon is not direct line, so like that. It says find me an interval. So L plus or minus that interval, L plus or minus epsilon, which is a specific number, gives us an interval. And we have to find an interval that matches that interval. That's literally what it means. So A minus epsilon, A plus epsilon. So simply put, find me a number that you can add to A or subtract from A that gives us an interval. So this interval right here that matches with this interval. That matches with this interval. So when we have to find an x interval that matches with the y interval. That's all it means. So here's how we'll do the proof. So let's give an example here, and we'll do limit as x approaches 3 of 4x minus 5. So any person would know, I mean, if you've taken, I guess, even pre-calculus, you would know that the limit would be 7 here. Because it's a polynomial function, and for polynomials you could just direct substitute because they're continuous all throughout. So pretty simple stuff there, nothing too crazy. Now the proof it's not rigorous, it's just, it's not unnecessary either, but it's just more so, like, you don't really see this, like, ever, but we'll plug the 3 in. So basically, remember that the notation was f of x minus L. Has to be greater than epsilon, or less than epsilon, sorry. And this thing right here will always give us the distance from L. So the reason why we use arbitrary values, and you'll see in your textbook, they'll just substitute the f of x function here, so 4x minus 5. The limit value, which is 7 right here, is greater than epsilon. So in confusion, you might say, well, then how would you know if it's epsilon if there's two variables that can be either or? So this can be some arbitrary number. How does that denote what epsilon is? And that's the beauty of it. You can choose x as any number, and epsilon will always be greater than that, and that will be the band of resistance. Then we find a delta that has the ratio. So if delta is 4 times less than epsilon, then that's the ratio. So if epsilon is like 500, then delta would be 125. Kind of the logic here. And again, we can factor out the 4 because 4 is just an amplifier here, an epsilon. So it's important to note that we go back to this root function here, 4x minus 5, and we'll do, let's plug in 5. So it will be 4 times 5 minus 5, which is just going to be 15. Note that if we minus 7, we get 8. So, and then we'll plug 4 times 5 minus 3 here. That's the same thing as 8. So notice that this is simply the formula to get the distance from the limit value. Simplified, that's all that is. But we also note that, remember, the delta definition is x minus a has to be greater than 0 or less than delta. And I keep drawing delta like this because I forgot what the symbol looks like. Actually, no, it looks something like a squiggly line, actually, like that. But notice a here is 3. So x minus 3 has to be greater than 0 or less than the interval value that makes this true. So if we come back over here, this is the same thing as 4 times the inputs, because the input is x minus 3, which gives us the distance from the a value, less than that. We rearrange this to get x minus 3 is less than epsilon over 4. So now we have two inequalities. X minus 3 has to be less than delta, and x minus 3 has to be less than epsilon over 4. So what does this mean? Now, all this means is that whatever this is, epsilon, delta has to be greater. And whatever epsilon is, this has to be greater. But note that we can just set delta and epsilon equal to each other, or delta equal to epsilon over 4. And why can we do so? Well, let's say that delta is not epsilon over 4. Let's say we denote delta, and we can denote delta as anything we want, because again, these are arbitrary values. The bigger delta is, then the greater epsilon will be. I mean, logically think about it, right? If you increase the x interval on a function graph, the y interval will increase typically, assuming the function isn't constant, and some other things. So yeah, that's what it means. Or if it's like a sine graph, I guess it wouldn't really change anything. But still, we can set delta equal to epsilon over 4 because it still fulfills the proof. I mean, if we compare these two things, like if we set this equal to epsilon over 4, it makes the definition true. Like, it makes these two things fulfill each other. So at most, delta can be equal to epsilon over 4. Delta cannot be greater than epsilon over 4. So delta cannot be equal to epsilon over 2, because guess what? If we plug in x minus 3 is less than epsilon over 2, this doesn't make sense because this has to be smaller than epsilon over 2, but then this has to be smaller than epsilon over 4. But we just proved that its maximum can be less than epsilon over 4. But then this is less than epsilon over 2, which means that it has a wider resistance band, and that is not what we want. So that's all that means. So let's go over the terminology one more time, and this time we're going to be a little bit more concise. We're going to set a function right here, and 4x minus 5. I'll draw it out this time. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. There we go. Okay, so we'll do 4x minus 5. And again, this is rise over run. I mean, you should have known how to draw lines. And we'll just draw a line here. That's probably inaccurate. So we'll come over here. And boom. A line right here. So if it's 7, and 7 is 1, 2, 3, 4, 5, 6, 7. Right here. I don't like this because I would have to draw this a little bit further. So if it's 7, and 7 extrapolates right here. We found the resistance band to be A plus epsilon over 4, A minus epsilon over 4, and then here it would be 7, and then that same interval band, 7 minus epsilon, 7 plus epsilon. So note that any other smaller delta value will work, because the inequality just states that the x minus a has to be less than epsilon over 4 here. But we can make this even smaller and it'll still be true. So it's kind of like if x is less than 5, then x is less than 3 is also true. Because if x is less than 5, then x is less than 3 is also true. So technically we can make the epsilon resistance value as small as we want. We could do x minus a is less than epsilon over 8, and it would still be true because all it does is squeeze the x value straight down. All it does is it squeezes. Sorry, I'm just a horrible drawer. All it does is squeeze this down, make it even smaller, and also makes this slightly smaller as well. So that is the logic behind the precise definition of a limit, and I hope this fosters understanding. So